All right, welcome to physics. We are moving on to section 11.2 today. We're only going to go through part of it. And there's more theory in this section than maybe in some others. We're going to talk about uniform circular motion. Now I will post the PowerPoint that goes with this. I couldn't think of the word for a second. I will post the PowerPoint that goes with this, but I do want to kind of talk about it myself a little bit and explain a little bit as we go. So they talk about, have you ever gone to like an amusement park or a fair or something, and they have a ride, sorry I have a dog that's spinning, they have a ride, could be called the Roundup. When I was a kid, sometimes they called it the Gravitron. But you get on this big circular thing, and there's usually like a pad behind your back, and you're not strapped into anything. And they start spinning it, and they spin it faster and faster and faster, and you feel like you're being pushed against the back of the ride where the pad is. Then not only do they spin it this way, then they start turning it vertically. And so you're spinning this way. And so even when you're up at the top of the spin, even though there's nothing holding you there, you don't feel like you're about to fall. You feel something pushing you against the back of that ride. And it's really kind of freaky. But the reason why you don't fall to your death is because of something called centripetal acceleration. Centripetal acceleration. So amusement park rides are only one of the very large number of examples of circular motion. Motors take advantage of this. Generators take advantage. Vehicle wheels, fans, a tornado or a hurricane, or even just a car going around a curve takes advantage of this centripetal acceleration. When an object is moving in a circle and its speed is constant, it is said to be moving with uniform circular motion. So if you're going in a circle, or some facsimile thereof, if you are going in a circle, all right, and your speed is uniform. You can't say that your acceleration is uniform, because even though you're not changing speed, you are changing direction. And acceleration is a change in velocity over time. And a change in velocity could be a change in how fast you're going, but it also could be a change in direction. So your acceleration is constantly changing when you're moving in a circle, or in a circular path, I guess was the word I was going for. The direction of the object's velocity is always tangent to the circle, which sounds really complicated but isn't. All it means is that if all of a sudden there was no force pushing you to the outside of that curve, say you were here, you would actually fly off in that direction. We've talked about this in terms of going around a curve when you're in a car and you feel like something's pushing you to the outside of that curve, and it's actually trying to make you go in a straight line, right? If there was no centripetal force, your velocity would you just fly off in a straight line wherever you were. You'd go off in that direction, or you'd go off in that direction, or you'd go off in that direction. You would just go off in a straight line. So the magnitude of the acceleration of an object moving with circular uniform motion is actually equal to velocity squared over the radius of the circle. Now they put a little c down here to indicate that that is centripetal acceleration. That is acceleration when you are moving in a circular path. It is your velocity squared over your radius. Now, according to Newton's law of motion, an object will accelerate only if there's a force to make it do it. If you need to accelerate, there has to be some kind of force to create that acceleration. So if when you're going in a circular path, you are constantly accelerating, that means there has to be some kind of a force there. That force we call a centripetal force. We call that a centripetal force. When you are accelerating, okay, when you are accelerating in a circle, you are always accelerating towards the center of the circle. Okay, no matter where you are, your acceleration is towards the center of the circle. So what is making you accelerate in that direction? Centripetal force is making you move in that direction. So centripetal force it's always directed toward the center of a circle. I have a dog fight going on downstairs. Hey! Okay. So since the force causing centripetal acceleration is always pointing towards the center of the circular path, it is called centripetal force. So centripetal force, F with a little c, is always going towards the center of the circle. The concept of centripetal force differs greatly from that of other forces that you've encountered. It is not a type of force like friction or gravity. It is instead a force that is required in order for an object to move in a circular path. Something cannot move in a circular path unless there is a centripetal force. Now, a centripetal force is supplied by or caused by another type of force. Why does something go in a circle? For example, we know that the planets move in a circular, not really circular, it's really oval, but we know it's an ellipse. But we know that they go in a sort of circular path. There's a reason why it's not perfectly circular. But it goes in a path around the sun. Why doesn't our Earth just fly off into space? Well, it's because there's a centripetal force pulling us towards that sun. But what creates that centripetal force is the force of gravity from the sun. So what about if you drive a car around a curve? It's centripetal force that keeps your car on the road. Otherwise, if there was no centripetal force, the road would curve, but your car would still go straight. That would be a problem. But what force creates that centripetal force to keep your car on the road? Well, that's the friction of your tires. That's why if it's icy and you don't have any grip on your tires, you have like summer tires on for some strange reason, your car does tend to go straight. So again, what about if I had a yo-yo and I was spinning it around by the string? What's keeping it going in that circular path is the force of tension between the string and the yo-yo. Now, it might just be one force that's contributing to the centripetal force, but it might be a combination of forces. Just like when we were talking about net force. Net force is the combination of all the forces. There could be more than one force that are contributing to the centripetal force. All right, so that's some of the theory. There is a formula for centripetal force. The formula for centripetal force is mass times velocity squared over r. That is your, because remember, force is mass times acceleration. That's what force is. And acceleration is v squared over r, v squared over r. So force is mass times v squared over r, mass times acceleration. That's why that formula is what it is. Makes sense, right? Okay, we're going to do two model problems starting at the bottom of page 555. The first one is not too complicated. The second one, the math is not complicated, but the theory behind it, we have to talk through a little bit. So, in number one, we have a car that has a mass of 2,135 kilograms. And it's going around a curve on a level road. Now it's important that that road is level and not kind of sloped. If you've ever gone on, well, I hope most of you have, on the highway and you go onto an on or off ramp, sometimes those are kind of tilted a little bit. Those are what we call a banked curve. There's a reason why that curve is banked, why it's kind of at an angle, and we're going to get into that later on in this section. But for now, we're on a level road. If the radius of the curvature of the road is 52 meters, radius is 52 meters, and the coefficient of friction between the tires and the road is 0.7. Wicket, stop causing problems. Wicket, I said no, come. What is the maximum speed that the car can take the curve without skidding off the road? It's important that people figure stuff like this out because that's where things like speed limits come into play. If you're on a country road and the road is kind of twisty, very often you'll see a sign that says curve up ahead, and it gives you a maximum speed that you can go around those curves. Well, guess what? They've done the math for that. Someone has done the math to figure out how sharp of a curve is it and how fast can the average vehicle take that. Now, they make it significantly lower than physically the car can do because they don't want you pushing it, right? Because they know if they put the maximum and you go a little bit over that and you skid out, they're going to be in trouble, right? So it's significantly lower. So when some of you say, listen, I've taken the curve a lot faster than it said, yeah, I know. That's because they're careful about those things. So how are we going to figure this out? So we are looking for the maximum velocity that the car can go. The formula that we have is centripetal force is equal to mv squared over r. Well, I have a mass and I have a radius. I'm looking for v, but I don't have a centripetal force. So I have to do some logical thinking. Sorry, Grace, I know you hate that. Every time I say logical thinking, you roll your eyes at me. So you're gonna have to do some logical thinking with this. So if a car is going around a curve, what is giving the car that centripetal force? What force is contributing to that centripetal force? Well, it is the friction of the tires and the road. So force, centripetal force has to be equal to the force of friction. Friction is the only thing keeping the car on the road. That's it. It's kind of scary when you think of it. So that means really force of friction is equal to mv squared over r, right? Centripetal force is equal to force of friction, which is equal to mv r squared. So what is force of friction? Force of friction is coefficient of friction times normal force, which is mv over r squared. So we said that the curve was on level ground. So if you have a car, it's my car, it's a very sad car. If you have a car on level ground, what force is pulling down? Well, it's gravity. So my normal force is just working against gravity. So my normal force is equal to my force of gravity. So coefficient of friction times mass times gravity is equal to mv squared over r. Now that I've set this up, now I can finally start putting numbers in. Now, notice I have a mass on this side and a mass on this side. If I want, I can put that value in. It won't hurt anything. But because I have an m here and an m here, it's just as easy to cancel it out. Less numbers I have to worry about. So coefficient of friction is 0.70. Gravity, 9.81, is equal to v squared, which is what I want to know, over r, which is 52. So 52 times 0.7 times 9.81 is equal to v squared. So I would take the square root of both sides, and I would find out that v is 19 meters per second. Okay, it's 19 meters per second. That turns out to be 68 kilometers per hour. Makes sense, you can go around a curve at about 70 kilometers an hour. So that's not an unreasonable answer. So that is how I would do that one. Again, you had to be able to figure out that your centripetal force was supplied by your force of friction there. That was the supposition, or that was the leap in logic that you had to do. All right. The next one is a little bit harder to explain in a way that makes sense. It makes sense in my head, but to get it out in a way that makes sense, I find difficult. So I'm going to take this relatively slowly. This is example 2 on page 557, and here's what it says. You are playing with a yo-yo, and I wish I had the yo-yo that Reed gave me, but it's at school. This is where I'd be pulling it out. I should have brought it back with me, but I brought so much stuff already back out of my cupboard, it's crazy. You're playing with a yo-yo. The yo-yo has a mass of 225 grams. So mass 0.225, okay? The full length of the string is 1.2 meters. So really that's a radius, and I'll show you why in a minute. And first, shut up! Thank you. Now that was sass, stop. Okay, now it says you decide, because apparently you are very bored in quarantine. Hey! Dog fight. Stop. Come up here. Come on. Rolly. Wicket, come. We'll see whether one of them comes or not. All right. So you decide, because you're in quarantine and you're very bored, to see how slowly you can swing the yo-yo in a vertical circle. So, you know, you're sitting and you're just doing this. How slow can you make it go and have it still go in a nice, perfect circle? Why are you doing this? I don't know. If you need something better to do, I can find it for you. All right, but that's what you're doing. So we want to calculate the minimum speed that you can swing the yo-yo. So this time not the maximum speed, but the minimum speed that it can go and still actually go in a nice perfect circle. And then it says, at that speed, when you figure that out, take that speed and determine the tension in the string when the yo-yo is at the side and when it's at the bottom of the swing. So we want the tension at the side, and we want the force of tension at the bottom. Now, in all model problems, they have this section called frame the problem. And I don't usually, wow, I don't know what they're fighting over down there. I don't usually go over that with you, that frame the problem section, because honestly, I frame the problem here with you as I go. But there's some important information in this frame the problem part on page 557 that I want to talk about. And this is the part that I find, I just haven't found the perfect way to say it yet, okay? So let's think about you swinging a yo-yo around in a circle, all right? And so the string is 1.2 meters. So that's the radius of this circle. Let's think about when the yo-yo is here at the top of the circle. We know that the centripetal force always moves towards the center of the circle. So, but we know that either a force or a combination of forces work to contribute to the centripetal force. So, what forces throughout the swing, what forces are working on that yo-yo? Well, gravity is pulling on the yo-yo, and the tension in the string is on the yo-yo. So when the yo-yo is at the top, force of tension is actually going this way towards the center of the circle, the same direction as centripetal force. Force of gravity is also working this way, which, oh my word, which also contributes. Now, if you're swinging it too slowly, then when the yo-yo's at the top, that string doesn't really have any tension in it. It starts to kind of go wobbly, and that's when the yo-yo falls to the ground, right? So if it's not going in a circle, if you're not going fast enough to keep it in a circle, then there wouldn't be any tension in that string, because the yo-yo would actually start falling because of gravity, and then there wouldn't be any tension in the string, okay? So what they say, and I'm going to read this to you, it's the second statement below the frame the problem with a little square in front of it, all right? I'll do that once they shut up. I love my house. I do. Love my dogs. I'm assuming my husband just came home. Yes, he did. I heard the door. That's why. All right, so point number 2 says, if the required centripetal force is less than the force of gravity, then the yo-yo will fall away from its circular path. So if the centripetal force is less than the force of gravity, it won't go in a circular path. If the required centripetal force is greater than the force of gravity, then that's when the tension in the string will have to come into play, okay? Because if the centripetal force is greater than the force of gravity, then force of tension also has to be working, all right? So, therefore, the smallest, this is the important bit, the smallest possible velocity would be the case where the required centripetal force is exactly the same as the force of gravity, okay? So, the minimum velocity is going to happen when the centripetal force is exactly the same as the force of gravity. So, to figure out part A, the minimum velocity that I'd have to swing that yo-yo around with, to figure that out, I know that that happens when the centripetal force is equal to the force of gravity. So, even if you didn't totally catch everything I just said, here's the part you really need to catch. The minimum velocity happens at the top of the circle when the centripetal force is equal to the force of gravity. Okay, so if you want to figure out minimum velocity, make your centripetal force equal to the force of gravity. And centripetal force is mv squared over r. So what is force of gravity? Force of gravity is mass times gravity times mv squared over r. Now again, you can put your mass in because we have one. You can put it in, but because you've got a mass on this side and a mass on this side, it's just as easy to cancel them out. So we have 9.81 is equal to v squared over r. We know that our radius is 1.2, so 1.2 times 9.81 is equal to v squared. So I'm just going to take the square root of both of those, and it turns out that the velocity is 3.431 meters per second. So paying attention to significant figures, I've only got 2 here, so that is 3.4 meters per second. If I don't swing that yo-yo at least 3.4 meters per second, then it's not going to stay in that circular path. All right, so that's the first part. So the next part of the question asks me 2 things. It asks me, what is the force of tension when the yo-yo is at the side? And what is the force of tension when the yo-yo is at the bottom? So we need, again, to kind of look at what's going on here. So the yo-yo has continued through its circular path, and now it's here, okay? So force of tension would be going this way, right? Because force of tension on the string is going to be going in that way. And force of gravity would be going this way. So what way does centripetal force go? Centripetal force always goes toward the center of the circle. So the only thing that's going towards the center of the circle is force of tension. Force of gravity is going completely perpendicular to that. And remember, we look at horizontal and vertically totally separately, which means that right now, at this moment in time, force of gravity is not contributing at all to my centripetal force. The only thing contributing to my centripetal force is the force of tension. So if I want to know what the force of tension is at this point in time, I would say that my centripetal force is equal to my force of tension, which is equal to mass times velocity squared over r, right? Because centripetal force is mass times velocity squared over r. Well, I just so happen to have a mass, 0.225. I now have a velocity, but don't use the 3.4, don't use the rounded off, use the full answer, 3.431, because then you'll be more accurate, squared all over 1.2. So that's just a matter of putting it into your calculator. Turns out that the force of tension is 2.2 newtons. Okay, so the force of tension is 2.2 newtons, because at this point, force of tension is equal to centripetal force. All right, third part of the question. Third part of the question now says, what is the force of tension when the yo-yo is at the bottom of the circle? So again, let's think about that. Force of tension would be going this way. Force of gravity would be going this way. Now remember, centripetal force is always working towards the center of the circle. Have I said that enough yet? I hope so. It's always going towards the center. But this time, force of gravity is also working in the vertical direction, just like force of tension and centripetal force, but it just happens to be working in the opposite vertical direction. So here's what I would say. I would say that my centripetal force, right, my centripetal force is actually equal to my force of tension minus my force of gravity, because they're going in opposite directions. They're working in opposition to one another. So remember, I'm trying to figure out force of tension. So force of tension would equal my centripetal force plus my force of gravity. Centripetal force is mass times velocity squared over r. Force of gravity is mass times gravity, and that would equal force of tension. Now it's just a matter of sticking the right numbers in. So mass is 0.225. Velocity is 3.431 squared. Don't forget to square that. A lot of people do. Over 1.2 plus mass, which is 0.225, times gravity, which is 9.81, which is equal to force of tension. So again, now this is a matter of just putting all that into your calculator. It turns out to be 4.4 newtons. So that is the tension that would be at the bottom. Your maximum tension in the string happens at the bottom. That's where the most, so if a question asks you to figure out how much tension does the string have to withstand, my husband's home, he can deal with that. If the question says how much tension does the string have to be able to withstand, well, it has to be able to withstand 4.4 newtons, because at the bottom, that's where your maximum tension is going to be, because it has to take care of the centripetal force, but it also has to take care of the force of gravity. So that's why, right? Because your force of tension is equal to your centripetal force and your force of gravity combined. All right, so hopefully I didn't lose you too badly in there. Like I said, I'll post the PowerPoint for this section. We only have, we have to talk about banked curves, which honestly doesn't take that long, and we will be at the end of this section. So I'm saying probably Friday for a test. That will make next week a pretty easy week. We will just have to finish up this section, and then I'll give you 2 or 3 days to ask questions and to study. And we'll do a test on Friday. Now, if Friday doesn't work for you for some reason, if you guys have like 6 tests already for that day, please let me know. I'm giving you lots of advance warning here. So please let me know if Friday doesn't work, but I'm saying Friday for a test right now, unless we need to change that. Okay? And that will finish up chapter 11 already. Yay, yes. All right. Have a good weekend.